Okay. How do we draw the phasor diagram of a three-phase transformer? If delta winding is there, then phase voltage and line voltage, what is the relation? Delta winding is there, then what is the relation between line voltage and phase voltage? We call this is the delta. This is the line.
VL is equal to root 3 VP.
VL is equal to root 3 V phase. See, this is the line voltage. It will be same up to here.
Delta VL is equal to VL.
V phase, yeah. And what about the current?
IL is equal to root 3 I phase.
Root 3 I phase, okay. In star winding, relation between voltage, VL is equal to root 3 V phase. And current will be the same, IL is equal to I phase, okay. Alright. After that, for drawing, you need to do that in delta winding, relation between the current is there, VL and V phase are same. So what we do, we first plot phase current IR by D 120 degree apart. Sequence should be same, that we do not discuss, but sequence should be R by D. This is the sequence. First R phase come, then Y, then B. Any two terminals or phase interchange, then their rotation comes into the motor, but we can say sequence will be reverse. Now what is the reverse sequence? See, here is the R, here is the Y, here is the B. So what is the sequence in this way? R, Y, B. Now if I say change two terminals or two letters, so it will become R, B, Y, these two. Okay, so see, R, B, Y, counterclockwise. Interchange these two, Y, R, B. See, Y, R, B. Anticlockwise. Interchange these two, B, Y, R. Oh no, not this one for anything. B, okay, yeah, that is for B, Y, R. It is also in this dimension. Okay, so you interchange any two letters from R by B, then your rotating pattern will be changed. Okay, got it? This idea? Or no? R by B is going in this way. You just change any two letters. Interchange any two letters, B here, Y there, anticlockwise. Okay, here we have changed R and Y. Here we have changed R and B. Okay, sequence will be reversed. Alright. Another thing is that what is the relation between line voltage and current or phase voltage and current? Here the line current is there. Here is phase current is there. So line current is higher here and it will be leading by 30 degree through the phase current. So that is going in this way, all the phases. So pink will be always leading to the white vector by 30 degree. Okay. So this is the overall idea regarding to the phasor diagram. Alright. Now quickly I am going to discuss all possible connections, alright, so that you can study those connections by yourself, because idea and fundamental has been clear, how to draw the phasor diagram and how to draw this kind of circuit diagram. Alright, so possible connection in three-phase transformers are, one is a star-star, okay, another is a delta-delta, another is a star delta. Fourth one is a delta star. Okay, these are the possible connections. Another new connections are there, which we call open delta connection. What we are doing there, we have three windings in delta in this way. Okay, we remove one winding, and with this three terminal we give the supply voltage. Operation will be changed. How much amount of the operation will be changed? What is the effect? It winding, if it is generated, then it will about 57.7% of the delta. One winding is being removed, so remaining winding will be 57.7%. How it is come? What is the derivation? No need to derive it. But you just need to remember that open delta connection is working on 57.7%, and sometimes it is called V connection also. Because it is look like a V when you remove one winding. Okay, from here also V, from here also V. So sometimes it is called V connection. Another connection is what we call Scott connection. You just need to remember this name only. In Scott connection, something kind of this winding will be there. Or sometimes it is called the T connection. Okay, so one terminal here, another there, third one will be here. And in that way, you have to apply the three-phase supply. And final one is called zigzag connection. Okay, what we are doing in the zigzag connection, that we will discuss, because that little bit tricky. So you need to remember these four types of the connection: star star, delta delta, star delta, and delta star. That is the most important. Okay. Now think about a star star first. You give three terminals, so one is here, another is there, third one is there, and that will be the line voltage. So whatever voltage you give line, inside each and every line, okay, here is a phase, phase and phase. Two phase together become a line. Those EMF, those voltage will induce secondary voltage in this line. This one induce here, that one induce here, and this one induce here. Collect those line to line. So whatever the line to line voltage you have applied, same line to line voltage will come out in star star. Okay. In delta delta, same thing happens. Here is a one terminal, here is a one terminal, here is a one terminal. You apply here whatever the winding ampere voltage here, same will induce on secondary side here. This winding will induce here, and that winding will induce here. This voltage is a line voltage which is equal to phase voltage, and that voltage is come out here. So here is also same voltage will come out. If any phase difference is there, no. No phase difference is there. Because whatever the voltage you give, transformer will on a star side is there, the line to phase voltage there will be 30-degree phase shift. But same will induce here, and here again from phase to line 30-degree phase shift. So in star-star connection, you will have whatever the voltage here, same will be here. In delta-delta, whatever the voltage here, same will be here. If transformer is 1J1, then. But what will happen here? Star to delta. This is, we have last time discussed. If I give supply here and here, okay, this is the line voltage, this voltage is a phase voltage, that voltage is a phase voltage. Phase voltage, both phase voltage will be less by the line voltage. How much amount? Divided by √3. Whatever this phase voltage, that will induce the secondary voltage in this winding. Whatever the voltage here, it will induce here. Whatever the voltage in this winding, same will induce here. 1J1 transformer is there, so same voltage will be there. After that, you collect it here, so that will be little bit less, √3 times less. Are you getting this concept or no? √3 times less voltage will be here. And vice versa happens here. If you given supply here, whatever the voltage here, it will apply to the phase. See, this phase will induce secondary voltage on that phase. This phase will induce here on that phase. This phase will induce here on that phase. And you collect it, then it will have a phase to phase voltage. That means it will be higher, root 3 times than supply voltage. Here it will be lesser, root 3 times than this supply voltage. Okay. And that root 3 times magnitude difference comes regarding to that phasor diagram that we have discussed. And whenever there is a root 3 times higher or less magnitude is there, then according to that, there will be the phase differences also there. Okay. So here in this voltage there will be phase differences also there 30 degree. Here the phase difference is also there by 30 degree. Line voltage always leading to the phase voltage. Here line voltage is always leading to this phase voltage. So this voltage is lagging this one, because this one star is leading. Here star is leading, so output voltage is leading, then input voltage. Output voltage is lagging, then input voltage. Okay, so this is the difference. Are you getting this concept first, or should I repeat it? Or I should go to in little bit deep? Should I go through the another drawing? Yes.
Yes.
Let's say this is the star. Let's say one giant transformer. Let's say this is the. I have put the animation on canvas, 3-phase transformer. Have you gone through it? See that it will give you a better idea. Okay, let's say it's R, this is Y, this is B. Line to line voltage is this one. And this one is also. And this one is also. Phase voltage is this one. R phase, B phase, Y phase. One giant transformer. Okay. Inside real operation, something like this. Okay. You will have here a first winding, then a second winding, no, a second phase, okay, and thereafter you will have here second winding on the same leg. This is called leg of the transformer. Okay. Primary, secondary. Whatever the white winding induce the flux, that flux through the core link through this over yellow winding. Okay, and it is 1 transformer, let's say. Then whatever the voltage that is given to this winding, same voltage will be induced on this yellow winding, secondary winding. Okay, so this is the phase of the primary, this one. Yellow winding is the secondary phase, so this one. Let's call it R, Y, and B. So we can say these two are on the same leg. These two are on the same leg. These two are on the same leg. Something like this. Okay. Same thing happens here also. Same thing happens here also. But you connected this winding in a star fashion. So this is my phase, this is my phase, this is also my phase. And these are the neutral, connect the neutral way together. So neutral connected, R, Y, B, R, Y, and B, something like this. So in between this you give the supply voltage. So that voltage is going into the two winding. That voltage is going into the two winding. Here it is white diagram. See the white diagram? It is going into the two winding. Okay? And that divided by the root 3. Because this is high voltage, phase is a less voltage. Whatever that voltage, it will induce in this yellow winding. So that will induce in this yellow winding. Okay? For the better understanding purpose, I can change this with the yellow winding. So you can read better again. And then you have to collect this. So it is incorrectly connected like a delta fashion. So what is the delta fashion? This is my phase, this is my phase, and this is my phase. So first phase, second neutral, second phase, third neutral, first phase, third phase, first neutral. Okay. And these are the three terminals. And these are the three terminals. So whatever this phase induced here, same voltage will be appear on the yellow winding. Whatever the white winding induced here, appear on the yellow winding. Whatever the white winding induced here, appear on the yellow winding. White winding is supplied line to line. So voltage divided, and each white winding has a divided by root 3 voltage. Same will be induced here, and same voltage will be appear at the output terminal because it is connected in delta fashion. So this winding induce the voltage, it will go like that and go like that. So whatever the voltage induced inside this winding, that will appear on the line voltage also. Because in delta fashion, phase and line are same. So here we see. So let's say I have V voltage, then white winding has, here V voltage is there, then white winding has V divided by root 3 voltage. Yellow will induce V divided by root 3. And it is connected in delta, so it will give same voltage, V divided by root 3. Okay, so line voltage, phase voltage, primary side, phase voltage, line voltage, secondary side, primary connected in star fashion. So line voltage is V, phase voltage is V divided by root 3. Okay, inside transformer, phase to phase action appear. So whatever the voltage here, it will generate here because of 1-1 transformer, and it is connected in delta, so same voltage will come out. So if you give input here and you collect output there, then supply voltage is V and output voltage is V divided by root 3. Clear? So it will reduce if it is star delta. And if it is delta star, then voltage will be higher. So you can say that from here to there. So if you give here a V voltage, it is connected in delta, so same voltage will appear on the phase. Phase has whatever voltage, it will give induction to the primary side. So same voltage will induce into white winding, so it will be V, and that is collected line to line, but it is star, so it will be root 3 times higher. See, V is root 3 times higher than V divided by root 3. Now here V voltage is there, then here is root 3 times higher. So going this way, and here going that way. From delta to star and from star to delta. In this way you have to understand. Okay. So this is the core concept that it will imply in real transmission line system. But whenever you do this, benefits are there and some drawbacks are there. Let's say when you apply star to delta, voltage rise or voltage fall by root 3 or multiply root 3 will be there. But there will be a 30-degree phase shift is also there. Okay? And 30-degree phase shift, what it will do, that you right now you cannot understand, but you have gone through laboratory that what current lag or lead inside the inductor inside the capacitor. Okay, so that lag and lead phenomena comes into this picture. Another important thing is that harmonics are there in real life. Now, what is harmonics? Harmonics, that means if I have sine wave, something like this, and that wave will become something like that. Okay, real life, this kind of the wave is there, not perfectly sine wave is there. Okay, so this kind of the waveform is actually can made up of pure number of different sinusoidal wave with different magnitude, with different frequency. Particular components are there, and if you add all those sinusoidal components very well, then you can get any kind of the distorted waveform. So pure sine added together perfectly, then it will give you perfectly distorted wave. What do I mean by that? You have a sine wave something like this, higher magnitude, lower frequency, higher magnitude, lower frequency, smaller magnitude, higher frequency, still smaller magnitude, higher frequency, still smaller magnitude, higher frequency. Okay. Now you need to add it. So add each and every peak to peak or point to point values all the way. And when you add all those waveforms, you will get this kind of waveform. If you change amplitude and frequency perfectly, you may get triangular. If you change here that particular frequency and magnitude, you will get square. Whatever kind of the magnitude waveform you can get it from like this. And this kind of thing is called Fourier series and Fourier transform. In mathematics, we will deal with this Fourier series. Okay, sigma cos n omega t plus sigma sin n omega t. Sigma goes from negative infinity to infinity. Sin goes also negative infinity to infinity, and you have to add it. Right now it is sin. You can collect plus, and then you can make all kind of cos waveform. Cos starting from this. So add this kind of cos, sine and cos waveform, you will get any kind of the waveform. But if you have this kind of waveform, you can extract what kind of the waveform hidden inside it. So from addition of all this, you can collect this kind of waveform. And if you have waveform and you apply same reverse mathematics, you can get this all the separate things. Okay? And the main component here is called fundamental component. It is nearly equal to this wave, and other things are the distortion, and those things are what we call harmonics. Okay, so this kind of harmonics are there in power system, and this kind of harmonics destroy the voltage waveform. Okay, so what engineers do, they will apply Fourier analysis. Okay, and they will see on the computer that how much amount of components are there. Third harmonic, fifth harmonic, that means 3 times higher frequency. Fifth harmonic, 5 times higher frequency. This kind of the harmonic, they will extract it. They will remove harmonic. And then they will connect this pure sine wave. Okay. Now what will happen if the third harmonic is there? Third harmonic, it means you have a 3-phase system, you have a 120 degree apart phase shift. But third harmonic, that means 3 times higher frequency. And 3 times higher frequency is there, then phase shift also 3 times higher. So 120 multiplied by 3 will give you 360. And 360 is in phase waveform. It is not out phase waveform. 360 is in phase waveform. So all third harmonic wave add together, then they will give you a large amount of the unexpected voltage. Okay, so in kind of this kind of transformer, if third harmonic is there, then third harmonic is in phase, so that will not going outside. say here to here, then some are there and here to here. But in phase is there, so they are in phase, so they are circulated in this way. Whatever current coming out from this winding, same will be going that winding at the same time. At the same time, same will go in this winding. 120 degree apart, this one will maximum after 120 degree, this one will maximum after 120 degree, this one will maximum after 120 degree, this one will maximum. But all the phase has no phase difference, then all are maximum at the same time. So it will give the current in this direction, this will also give current in this direction, this will also give the current in this direction. So third harmonic is there, then it will circulate here, and number of third harmonics higher, then the current is also higher, and that will circulate into the delta winding. So in some practical, you want to avoid third harmonic. In that such kind of system, you have to put delta on the secondary side. If you put star on secondary side, okay, then because of that third harmonic, because it is in phase, this winding maximum voltage comes in, 2 are exact should equal and opposite. So half of the magnitude, not equal and opposite, half of the magnitude and opposite. So half of that going in this way, half of that going in that way. So whatever current go in, half of that should be in this direction, half of that at the same time should be in this direction. And that things happens if all three wave has 120 degree phase shift, like this. But if they have no phase shift, then whatever the current comes in, the same current is also going and same current goes also in. Okay. So at that time, we can say this voltage give the supply in this way, this winding is also give the supply in that way, this winding will also give the supply in this way. Because all three winding are in phase. Some generate the voltage and go into the particular point. All three winding doing this. If this winding has a negative voltage, then this is also has a negative voltage. So at that time, all the three phase third harmonic, because third harmonic is in phase, so that will appear on this point. And this kind of the thing we call, this is the neutral, we call neutral shift. Neutral should be 0, but now if third harmonic is there, then neutral has some extra voltage. And if the neutral has some extra voltage, then it is under the stress, it is under the voltage condition, stress voltage condition. Okay. So delta winding is there and third harmonic is there, then current will circulate inside this winding. Star winding is there, then voltage of that third harmonic will appear here. And you connect some load here, then that third harmonic current will flow here. Okay. And sometimes third and fifth harmonics are too much pronounced. Okay. That I am not going to go into the detail that what is the harmonics. Even harmonics is there, odd harmonics is there, third, fifth, seventh, ninth are there. Okay. Then second, fourth, sixth, eighth, even harmonics are there. Third, fifth, seventh, ninth. Inside that, multiple of the three is very well affected. 3, okay. Then 9, alright, and go on in this way. So this kind of the thing is there. So whenever they ask you that explain the three-phase transformer different connection, then you need to draw these connections. Okay, immediately with this diagram. Immediately below the diagram, you need to draw the phasor diagram. Okay, and after doing that, or you can draw just star and delta winding in detail. Draw the star phasor diagram, draw the delta phasor diagram below that drawing, and on the next page, star star explain something, delta delta explain all those things, star delta star. Okay, in this way you have to explain this core connection. And then open delta and chord connection and zigzag connection, you go through it. If you understand it, then you can write down it. Otherwise, you can leave this. Okay? Because at the first year level, this is little bit confusing. What they do in zigzag winding, that I am going to just mention you. It will collect here one winding, it will go here, it will give the winding here. Okay. Then they will collect another winding from here, they will go there and here. They will again go in this way and here. In this way, you will have two windings in a one phase and second winding coming out from the this winding. So in this winding, you take the connection and give the opposite magnetic field winding on top of this. So here you see, then here the secondary winding is there, then take the connection from here, okay, put another yellow winding, and that yellow winding has opposite turns to this yellow winding. So this winding will give out of direction flux, then this will give inside flux. Okay. And this kind of the things has been done to compensate that phase shift. 30-degree phase shift is there, star to delta. If you want to compensate it, then you can use zigzag winding. Okay. So this is the zigzag winding, Scott winding, open delta winding, and star and delta. Star and delta is a full configuration, and another winding. So this is the end of the story of transformer. Okay, connection, working principle, single phase, three phase, all those things. Comfortable with that? We can start the next chapter right now because we have to understand machine also. Okay, so if you go through the book, then there will be very well in detail drawings and explanation of that. But now you are capable to understand it. Now you read, then it will not look like that it is something difficult. You can now understand it if you see the book. Okay. All right. So this is the idea of three-phase transformer. No need to write it down this whole thing because the lecture is already recorded. So you can see on the YouTube and you can take the class note. Okay. So now we are going to deal with the machine, electrical machine. So transformer is electrical machine, yes, but it is its working and its operation is so complicated that we need to understand as a separate chapter. But in your first year, all the machines are given into the single chapter. So how many different types of the machines are there? Well, transformer, generator, and motor. If you go into the motor and generator, then it will be AC motor and it will be DC motor. It will be single phase, it will be three phase. If you go into the generator, it will be single phase, it will be three phase, it will be AC, it will be DC. Okay. So if machine is there, machine is there, the types are like according to DC and according to AC. Then motor will be there, generator will be there, motor will be there, generator will be there. Motor will be single phase, three phase, generator will be single phase, three phase. Here is also single phase, three phase. Here is also single phase and three phase. Okay. Another connection is there in motor and generator. It is because of the connection of the stator and rotor winding. So stator and rotor may be connected in parallel and may be connected in series. So series generator is there, series motor is there, parallel generator is there, parallel motor is there, and compound is also there. Combination of series and parallel. Three-phase generator is generally called alternator. Three-phase motor will have synchronous motor, and three-phase induction motor. And here single-phase induction motor. Inside single-phase induction motor, there will be a 3 to 4 type of difference motor. Here only two motors are there. squirrel cage, and here is a wire one. Okay. So this is the broad classification of the electrical machine. We can say DC machine is there, operate on DC supply, operate on AC supply, generate DC supply, generate AC supply. Motor generator, 3-phase, single phase, motor generator here, 3-phase or single phase. So these are the motor. Synchronous motor is there, 3-phase induction motor is there, and 3-phase induction motor has a 2 types. Squirrel cage or wire rod. Single phase induction motor types we will see capacitor, run and capacitor on motor is there, capacitor start, capacitor run motor is there. Okay. Those motors are used in this phase. That is the working of the single phase induction motor. And then there will be 3-phase generator which is alternator. Okay. Single phase generator is also there, AC. So in your syllabus right now, what are the main important questions? This one, okay, 3-phase induction motor, this one, alternator, and wait, in DC machine 3-phase is not there. In DC machine only motor is there and only generator is there. That's it. Then it will come that parallel and series. Here is also parallel and series. 3-phase concept comes into the AC only. In DC 3-phase concept is not there. Okay, and here a simple motor and generator. 2 things are there that you need to study. So we are going to study all these machines step by step. Alright. Okay, so let's start first. 3-phase induction motor. Okay. Now recall the concept of rotating magnetic field. Do you recall that concept? Rotating magnetic field. What we have done? Rotating magnetic field. What is the meaning? Full form? It is a full form rotating magnetic field. Short form is RMF. Rotating magnetic field. MMF is a different thing. It's a magnetomotive force. RMF is a rotating magnetic field. What it will do? 3 coils are there. Inside that space, there will be the rotating magnetic field. First maximum this coil, then that one coil, then that one coil. Niyati. Name is a rotating magnetic field concept. 3 windings are there. Concept of rotating magnetic field. Let me quickly give you the recall. If I have here one coil, if I have here second coil, and if I have here third coil. Okay, this one is R, Y, and B. This one is this one, Y and B. This one comes the maximum after 120 degree. There will come the maximum after 120 degree. This one will come the maximum. So this one has a maximum flux in this direction. After a few times, this one has a maximum flux in this direction. After that, this one has a maximum flux in this direction. So we can say that magnetic field is rotating in this way. Okay. And if I have here a rotor, then it will create a rotating magnetic field will create EMF inside this rotor. Okay. So how do we understand it? before that we need to understand actual construction of the rotor. So I am going to discuss with this squirrel cage rotor. Squirrel cage rotor. How does it look like? Something like this. Okay, this is the ring, metallic ring. This is also metallic ring inside that. Okay, here is a shaft. This is what we call shaft. Okay, and then we have a conductors, but something like this, little bit inclined. Okay, and this is called end rings. End rings. This is called conductors, or we can say conductor bar. Okay, all right. And if I draw this structure something like this, and their bars are skewed little bit, but if I draw very straightforward parallel, something like this. Okay. So this is the structure of the squirrel cage rotor, and it is look like a cage. That's why it is called squirrel cage rotor. Okay. Now what will happen? See here. This is the main phenomenon that you need to understand. If I have here a rotor, something like this. If I have here a rotor, okay, and this rotor has a conductor here, something like this. Remaining portion is the insulation. Okay. The metallic conductors are here, right? And on the top of this, I have a metal ring. At the bottom of this, I have a metal ring. Okay. So metal ring at the bottom, metal ring at the top, and they are connected by the conductors, or we can say aluminum conductors. Okay. I have a magnet here. N pole, S pole. Okay. Now what will happen? See, if I rotate the magnet in this way. Okay, I rotate the magnet in this way. So from N pole, magnetic field coming out of the N pole. So it will go in this way. When I move my magnet in this way, so these parallel conductors will experience the cutting process of the magnetic field. Because magnet moves, conductor steady, but we can say relative to each other, conductors are moving into the magnetic field. So this magnetic field cut the conductor. So according to Faraday's law of electromagnetic induction, there will be EMF inside this conductor. Okay. So let's say here is an N pole on this side. Okay. And exactly I have two magnets. One is here and another is exactly opposite there. And this has an N pole here and another magnet has an S pole there. So total inside this rotor, N to S magnetic field will be there. Okay. And both magnet will rotate simultaneously in this way. Okay. So I can say that if I have N magnet here and S magnet here, then both magnet will rotate like this. Okay. Inside that conductors are there, they will experience the magnetic field cut the conductor. Now what will happen here is that inside that conductor, because of EMF will be induced. One is an N pole, another is an S pole. Rotation will be same. So one will give the voltage in this direction, then another will give the voltage in that direction. So what will happen? Because of this voltage, current will go like this. But here ring is metallic, so current will divide into the two part. That will collected here, okay, and it will go to this bar. Why? Because inside this bar already there is a voltage and current that is in this direction. So first conductor will force the current in this way, another conductor force the current in that way, so they will loop each other. Current will go from here, divided into the two part, collected again, go here, bottom side, divided into the two part, circulated, collected here and going like that. Clear? This is happening when magnetic field comes here. Then this is the story of these two conductors. Okay. Then the picture comes that magnets are in this direction and that direction. Alright. So that here is the N pole, here is the S pole. So in this conductor, current will go upside, divided into the two part in the ring, collected here, go downside, divided into the two part, circulated, collected, and going this way. Okay. So inside this all we can say all these conductors, the current will flow like this. Here is the current maximum going in that way, collected here, going in that way, collected here. So current will go like that, it will circulate, divided here, and the dotted line comes here. After that, it will divide it here, come back again on the ring, it will divide it here, circulate, come back on the ring and going this way. Okay. So this is the idea. Any question? We do not pass the current in rotor. What I say, according to Faraday's law of electromagnetic, voltage induces in this conductor only this portion. Voltage induces in opposite conductor only small portion. So voltage induces, we do not supply any voltage to the rotor. Here, if this is my rotor, let again go back to the squirrel cage rotor. If this is my rotor, okay, and here are the conductors, something like that, and magnetic field moving around this rotor. Okay, so cutting process is induce the voltage. That is the generator action. Right now we are dealing with the motor, but the thing will come that you will understand that generator and motor action both are there in motor and generator. If motor is there, then motor action is also there, generator action is also there. If generator is there, even though there is a generator action is there and motor action is also there, but slight difference between them. So one effect is higher, then machine is called motor. One effect is higher, then machine is called generator. What do I mean by motor action and generator action? By electromagnetic induction or that law, if the voltage induces, that is called generation part, because electricity induces. By somehow two magnetic field cross each other and give the force, that is the motor action. That we need. We need force, we need rotation. Rotation, that means motor. And we need electricity, supply, that means generation. Okay. So whenever there is a generator or a motor, both kind of things are there. You want to generate electricity, there will be the opposite motor action is there. Okay. When there will be the motor is there, you want to rotate the motor, rotation will give back you generation of the electricity. But that generation is less than supply voltage. Okay. Inside the generator, electricity is there, and then opposite motion is there, but opposite force is less than whatever the force you give to rotate this shaft. Okay. So in this way, in this bar, voltage is induced in this aluminum conductor, and because that induced voltage, it will in this conductor up to here portion, let's say voltage in this direction, in this conductor in this portion voltage in this direction. So this small portion behave like a battery at that moment. This small portion of the conductor behave like a battery at this moment, and two batteries are connected in series with this kind of structure. Are you getting this? If here it is going in this way, in this way, in that way, it will divide, it will collect it here, it will go up there and go in this way. So here current is in this way, it will divide into the two parts, here and there. This current will go completely like that. Here they both collected, going in this battery, here they divide into the two parts. This will completely go in this way. On this point they are collected and going back in this way. So this is the collection of the current at this point, this is the separation of the current, this is the collection of the current, and this is the separation of the current. Okay? So this kind of the thing is there. I can represent like this also. Let me make the better drawing then. So here it is supply current divided into the two part, collected here, divided into the two part, collected here. And where does this flow battery come from? That is momentary. That is because of Faraday's law of electromagnetic induction. Because in these two conductors, rotating magnetic field is there. That magnetic field cut this conductor. So this portion is behave like a battery because voltage is generated. And if two voltages are there and they are connected in this manner, then circulating current will go. Going in this way, divided into the two part, going back, divided into the two part, again. So this process will continue. Are you getting this idea? That will happen in this kind of squirrel cage rotor. But whenever there is a rotor and whenever there is a rotating magnetic field around that conductor. And I explain you the rotating magnetic field by permanent magnet. And we have discussed that if you do not have permanent magnet, if you have steady 3 coils, if you give well and define this kind of a supply, if you oriented all 3 coils in 120 degree apart, then also there will be the rotating magnetic field. So now what you have to do, you have to put 3 coil, rotor, give 3-phase supply, alright, and then automatically there will be the induced EMF inside rotor. Okay, this is the 20% portion of the induction motor to understand how does it rotate. So up to now it is clear, rotating magnetic field is there inside the rotor, voltage induced, and rotor conductor are closed circuit by clamping of the end ring. Rotor conductors are closed circuit by clamping of end rings. If extra conductors are there, here and there, here and there. Even though it will be something like all the conductors are short circuited by the end ring. Okay. So there will be the current. Okay, and there will be the current carrying conductor inside this rotating magnetic field. Okay, now next step, what will happen? Next step is that stator, that means out of 3 coils, this is called stator. And this is called rotor. Consider only this portion. Okay. And coil is bound like this. Another portion is there, second coil. Another portion is there, third coil. Okay, and there will be the rotor. Consider the rotor on this portion only. Only this picture. Okay, this kind of rotor. And that rotor has this bar. Okay, so this kind of the bars are there. So what do I mean by this? That this is the rotor, this is the shaft looking in this direction, and these are the conductors. These conductors. Clear? Picture is clear? If I extend in 3-dimensionally, then you will see this. This kind of rotor is there, squirrel fish, and they are skewed, not perfectly parallel skewed. That we will discuss later. Why this happening? It's an engineering trick that you want better sinusoidal operation, then you have to put this skew. But right now consider they are parallel. Okay, and the pole is here. So this is the picture. And this is the picture of the pole, rotor. Another winding is 120 degree here, and another third winding is 120 degree from there. So this is the 3 windings. This is the rotor, and we are only now focusing on this part. Okay, and here is that part. Right? Okay. Now let's say rotor is moving in this direction. No, not rotor. Magnetic field is moving. Initially rotor is steady. So from coil, magnetic field coming out in this way. Okay. And this whole magnetic field line will rotate, something like this. Okay, because of this process that we have discussed. And the conductor will see that magnetic field going in that way. Okay, so this is the first picture. Now second picture is that. Because magnetic field going in this way, magnetic field traveling in that way, so we can say that relative to the magnetic field, this conductor traveling in this way. Am I right or wrong? Relative, simple relativity. If I have magnetic field here, if I have a conductor, if magnetic field going this way, so that I can say that magnetic field is steady, equal and opposite speed of the conductor in that way. Or no? Wait. If I am on my bike, okay, I am going with 40 speed, okay, and some other person, Nemiso is on his bike, he is standing face to me, I am going in that way 40 speed, 40 kilometers per hour. What I will see? Nemiso going that way. That's what I see. But equal and opposite is also true. If I am steady and Nemiso come towards me with the 40 km per hour speed, even though I will say that yeah, Nemiso going in this way. So if I am traveling in this direction and he is steady, if I am steady and he is traveling to me in opposite direction, both the scenario will be same. This is the simple relativity 11 science. Not Einstein, general and special relativity. That's different thing. Special and general theory of the relativity. And this kind of the thing you have experienced if you have ever studied or traveled through the train. If you sit here and suddenly your train speed up, even though you will see that my adjacent train is moving in this direction, But then you take the reference, you see the land or you see something else. Then by comparison of the three portion, you can get the idea that how is actually moving. And according to relativity, in this universe there is no such experiment that someone is moving and someone is steady. That's not possible. There is no such experience or experiment if two planets are there and two planets going in the same velocity with this direction, okay, then 2% of the planet will see that this planet is steady and this planet person will see that that planet is steady. They have no experience, okay, and you throw the ball up and down, everything will look like this. No, because ball is also moving in this way, you are also moving in that way, okay, your whole colleague are also moving in that way, so everything will be the steady. Just like Earth is moving around the sun with 235 km per second. Can you imagine that? 235 km per second. You count one, 235 km has been traveled by Earth. But we do not notice. Why? Because everything is traveling at the same speed. Okay, so this is the phenomenon of relativity. So if I have a conductor here, magnetic field going in that way, or if magnetic field is steady, and conductor going from this way, both the things are same. Alright? And we need to consider only and only conductor motion. So that rule is for right hand three fingers rule, but I am not going to use that because it makes very complicated theory. So let's say this is the magnetic field that is rotating. Okay, and rotating magnetic field travel in this way, okay, so that will induce EMF inside this conductor, but conductor are closed circuit. Why? Because they are clamped by the end rings. And then if I will apply that rule that magnetic field in this direction, conductor moving in this direction, actually conductor is not moving, but I say that relative to magnetic field it is moving in this direction, then my EMF, okay, EMF will middle finger coming out of the blackboard, and that is dot coming out from the blackboard. If current is coming out from the blackboard, then I have to put thumb rule to get the circulation of the magnetic field around the conductor. So this is the thumb, this is the curly finger, and this is the magnetic field. Okay? This is the magnetic field inside the conductor because of this magnetic field rotating relative to this rotor bar. And that happens because of electromagnetic induction. Now what we have to do, here is the one magnetic field is already there. And another induced magnetic field like this. Now see carefully, what will happen in the direction of yellow magnetic field and white magnetic field? Both are in this way, here. What will happen here? Both are in opposite direction. Correct? What will happen here? Yellow line will go in this direction and white line will go in that direction. What will happen here? Yellow line is going in this direction and white line extended into the bottom direction. So I have 4 points. One is in this direction, circulation. Another is in this way. Another is in that way. Another is in this way. Now these are the magnetic field. They are vector. They follow the vector addition rule. So I will add vector at 4 points. Then I will get idea that what happened into the space each and every point. So this is my point 1. This is my point 2, 3rd and 4th. 4 points are there. So here yellow and white vector are same direction. So resultant will be higher. So resultant will be higher. Here yellow vector and white vector are opposite, let's say equal and opposite. So here 0 vector, resultant is 0. In this direction, yellow vector is in this direction. Tangent, I am going to consider only this tangent. Yellow vector in this direction. So what is the tangent? This is the tangent. And white vector is here. So my pink vector will go in this direction. Okay. What happened here? Yellow vector is in this direction, tangent, and white vector was already in this direction. So I can extend it like this. So my resultant will be here. So see, you have to join this line like this. Okay. And now all those pink vector are joining this way, and then they will go in this way. So if you draw each and every line of the yellow and white, then you will find this. Because this is the empty portion, alright? And here is the magnetic field of the rotor, and that rotor is here at the middle of this shaft. Rotor shaft is here and rotor is somewhere here. No, not rotor shaft, sorry, this conductor. This conductor that is in this way. And magnetic field, resultant magnetic field lines are like a rubber band. Okay, so if I have a rubber band, let's say this kind of a rubber band, I have also explained this phenomena. And then what I will do, I have some material and I go in this way. So on the top of the rubber bands are 2. At the bottom, rubber bands is 0. So rubber band will push from top to bottom. Okay, so concentrated rubber bands or magnetic field line will give the push on the material into the less concentrated magnetic field line. So this pink concentrated magnetic field will give the force on this direction. Okay. The key thing is that this portion is rigid and this portion is movable. So the force in this direction, so conductor will go in this direction. If this conductor has a force in this direction, let's say, okay, adjacent conductor has a force in that direction. And here is this also. If you complete the circle, then at the bottom, here is the N pole, there will be the S pole. S pole magnetic flux coming in this direction. Sorry, in this direction. And at that, conductor will experience opposite direction force. Here conductor force is in this direction, bottom of that force in that direction. So all the force on the conductor will give rise to the rotation. So we can say that each and every conductor has this kind of force. Here is a 0 force. Okay, then force increases. Again the times comes that it is reduced. Here is this direction. If 2 holes are there, okay, and in this way rotor will rotate in this direction. Because conductor experiences the force in this direction. This conductor under that pole. Another conductor here under the second pole will experience force in this direction. You add these 2 force, the rotor will rotate in this direction. That is the omega. So now picture clear. How does rotor rotate? 3D question. How does induction motor work? In this way, 3-phase induction motor does the work. Okay. So here is the 3-phase winding is there. Rotating magnetic field is there. Here is the rotor. Rotor has this kind of structure, end rings is there. Okay. Rotating magnetic field cuts the conductor, and conductor induce the EMF. Same opposite conductor, opposite magnetic field conductor has also opposite induced EMF. Those clamped with the end rings, current will circulate. That circulating current will create another magnetic field inside rotor conductor. Rotor magnetic field and stator rotating magnetic field cross each other. By the vector addition, we can say that it will experience the force and it will start to move. Okay. But simple thing is there, very simple thing. In whatever direction rotating magnetic field is there, you apply all the rules. rotor will also move in the same direction. Here rotating magnetic field in this direction, rotor will move in this direction. If the rotating magnetic field in this direction, rotor will move in this direction. And you can apply all these rules and you can check it. Okay. So this is the idea behind squirrel cage 3-phase induction motor. But wait. What rotating magnetic field has, let's say, RP, that is not visible. Rotating magnetic field is like magnet, it is rotating like this. So rotating magnetic field has also speed, fictitious speed, kaल्पनिक speed. Rotating magnetic field has also speed. Let's say rotating magnetic field rotate with 3000 RPM. Okay, we can see it. No, 3 coils are there. You give 3-phase supply, it will start rotating. How does it rotating? What is the speed? That will define with the formula that will come later. Okay. But if it is rotating with the 3000 RPM, does rotor also rotate 3000 RPM? Does rotor rotate less than 3000 RPM? Does rotor rotate higher than 3000 RPM? What do you think? Are you getting my question? Rotating magnetic field is there. It has a rotating speed. How fast it is rotating, how slow it is rotating. I told you that it is rotating 3000 RPM. 3000 revolution per minute. Then rotor will start to rotate by this one principle. And it will experience force and it will start to rotate. So what is the speed of rotor? Equal to 3000, less than 3000 RPM, higher than 3000 RPM. Less than? How? Any clue? The answer is right. 0 is not possible, 0 speed. If someone stuck the shaft, then it will have that it has a 0 speed, otherwise it will start to rotate. But it has a less speed. That's true. Equal to 3000 RPM? Yes or no? No. Higher than 3000 RPM? No. Less than 3000 RPM? Okay, then how? What? Weight on the mass of the rotor? No. That is the one key point that yeah, it has a mass, but go into the space, okay? Then the rotor will float. Space has no gravity. Okay. Put the 3 coil, stuck the coil, give the 3-phase supply. Rotor will start to rotate. It has a mass. It will take a time to rotation. But once it starts to rotate, it will remain in rotation forever. The mass will not be a problem. Even though I am telling you that if you go into the space, 3000 RPM rotor speed will not achieve. May achieve, let's say, but some important phenomena happens. Think about it. For that, hint is that let's assume that rotor achieved 3000 RPM. Then what will happen to the Faraday's law? How does rotor induce the current?
Magnetic field line
Current?
cut.
A cut thase magnetic field line of the rotor, rotating magnetic field, does not cut the conductor. Why? Because both are rotating, conductor and magnetic field line, both are rotating with 3000 RPM. Magnetic field line here going in that way. Conductor here, it's initially steady, but once it is in this direction, then it will experience the force, it will start the moving. And once the point comes that both will rotate at the same speed, no relative velocity. No relative velocity is there, no cut action. No cut action, Faraday's law, magic show is over. No Faraday's law, no EMF. No EMF, no conductor flux. No conductor flux, the remaining white flux is there. Yellow flux is not there. If two flux is not there, push is not there. Push is not there, then further rotation is not possible. So if push is not there, then rotor is freely rotating on the bearings on Earth. Freely rotating on the bearings. And bearings has a friction. So that will come down to slower the speed. 3000 rpm is there, then it will maybe 2900 rpm. Okay. And once rotor slow down, then there will be the relative velocity between magnetic field and conductor. If relative velocity is there, then again cutting process is there. Again it will, by this process, give the force. Again it will reach to the speed. No EMF is there, no magnetic field of the rotor, no force is there. Okay. So in this way, it cannot achieve anyhow to rotating magnetic field. Okay. Into the space concept, if you have a three-phase winding, if you have a rotor, and rotating magnetic field is 3000 rpm, your rotor will start to rotate with 3000 rpm. Then both are with the same rotating speed, both have no relative velocity, no extra electromagnetic induction noise there. Now you do not need three coils. Remove the three coils, rotor will rotate forever and forever 3000 rpm into the space. Into the earth, bearings are there. Bearing will slow down. Bearing will slow down, so again conductors and rotating magnetic field has a relative velocity. So initially relative velocity is high. Why? Because conductor is steady. When rotor start to rotate, relative velocity is very small. Clear or no? Initially conductor is there, steady. Rotor is not rotating. Rotor is not rotating. Conductor is really steady. And rotating magnetic field is at 3000 rpm. What is the relative velocity between RMF, rotating magnetic field and conductor? Maximum. Magnetic field going in this way. Once rotor starts the rotation, then relative velocity will be reduced. Now clear again. If I have a magnet, I have a conductor, I move the conductor. Relative velocity is maximum. I move slowly magnet and then conductor. Relative velocity is there, but less. Okay. So initially maximum EMF induced inside the rotor because relative velocity is high. Rotation time, relative velocity is low, so small amount of EMF is induced. Small amount of current is there. Small amount of ferromagnetic field is there. Small amount of force is there. So that small amount of the force that we need, that is actually applied continuously, equivalent to bearing loss and other loss, mechanical loss. Okay. So this is the whole idea behind three-phase induction motor. Next time we will discuss that relative velocity is called slip. That rotating magnetic field speed is called synchronous speed. Yes. Rotor speed is called N. Okay. And slip is a relative difference. So slip is given by Ns, rotating magnetic field, minus rotor, that is slip, relative velocity. And sometimes we will take it with respect to this. So it will become between 0 to 1. Then we need to multiply with the 100 for percentage. So this is called percentage slip. Difference between these two. Okay. But the key thing is that you have to clear this idea of the motor. That how does rotating magnetic field created? Because of this supply, we give this kind of supply here. Because of all those vector addition, rotating magnetic field is there. Now there is a rotor, there is a conductor. Okay, and there rotating magnetic field, we have to use Faraday's law of electromagnetic induction. Because of that, there will be the generation of the voltage. In generation of the voltage, there is a current. Current is there, another magnetic field there. Two magnetic field cross each other, it will give the force. So this is the motor, yes. Inside the rotor, generator action is there, yes. voltage generated, yes, inside the rotor voltage generated, then current will comes into the picture. And here to the rotor, no electric supply needed to feed. Only electric supply given to these three coils. Okay, no electric supply will given to the motor. In DC motor, you will see that magnetic field is there. Current carrying conductor should be in magnetic field. Then and then it will experience force. But here current carrying conductor is not there. Current itself induced inside this rotor because of that rotating field concept. And then interlocking the two magnetic field, it will get the force. Okay, so this is the complete picture of a three-phase induction motor. Alright, single-phase induction motor is also there. Only two coils are there, no three coils. Single-phase supply is also there. Okay, even though it can start the rotation that we will discuss later. Up to now, everything is clear. Or need any question, then you can ask. અત્યારે તો એ થાય છે કે આ બધું નવું આવ્યું છે પહેલાં તો એ તો સમજવા તો પછી ક્વેશ્ચન કરીએ પહેલાં સમજીએ આપણે પછી ક્વેશ્ચન થશે ને once you understand it then question comes because these things are totally new concept but I have given you the conceptual thing. Now whenever you read the book the thing will look like a familiar. Okay, એવું નહીં થાય કે મને એમાં કંઈક ખબર નથી પડતી એવું થશે કે આમાં કંઈક તો છે તો જાતે કંઈક વાંચી શકશો. Alright.